for NITI is, you know, NITI about condition monitoring, industrial engineering and maintenance. They are the leader in, actually the one time everybody was talking about industrial engineering, maintenance and condition monitoring means NITI. Now there are plenty, you may find. You know, NITI about an EDP program on maintenance. He was a life fellow of IIP. He's now life fellow of IIP and senior member of IEEE USA. And he is a founder fellow and chair membership of our Council of Vibration Specialists. So this is in short about him. We're going to learn more about him today and his lectures. Thank you, Mukesh sir, joining us. Over to you, Mukesh sir.
Thank you very much, Pine sir, for introduction. Friends, as Pine sir said, you know, this topic, condition monitoring of machines, is something which I will be speaking about today. I'm sure that there are a lot of participants here who are in this subject in depth, and maybe this will be something where, you know, it is just starting. I mean, I would say that even a person who has not heard about condition monitoring, I mean, I thought that let us start from that, because we really don't know who are the participants in this case. So I've picked it up in a right from the absolute basic. So my tagline, which I say that machines talk, let us listen. So it is something like, you know, for example, if you go to a machine and tell the machine, how about a cup of oil? Would you like it? And if the machine says, yes, I like it, or it says, no, I just had one and I don't need anything more. So can we do that? So in general sense, yes, this is possible. So let's look at it from that viewpoint. We will start from absolute scratch and we will build it up. And I'm sure that subsequently in upcoming days, we can always have more in-depth, seminar on this subject to learn more and more about it. It's a vast subject, and I'm sure that, you know, we can go into details step by step. Okay, so what I am going to basically do is, just to make it very simple, let us look at how do we compare it with medical field, you know. So I will be talking briefly about it. And then we talk about different types of maintenance, then which maintenance to choose, cost and benefit of predictive maintenance. The condition monitoring is, you know, primarily a predictive maintenance science. So we will do that. We'll talk more about predictive maintenance, different types of technologies which are used for predictive maintenance, like ferrograph, wear debris analysis, vibration monitoring, etc. Of course, we are going to talk more about vibration monitoring. And then we talk a little bit about what are the things what are we talking about. You know, so vibration amplitude, the ISO standard, the trend and frequency analysis, something Fourier transform, what is the general guideline for diagnostics of machine, and something about vibration monitoring instrument. So these are the things which we will be talking today. So let's say with the medical world, you know, so I've tried to show both sides of it. So if you see there's a doctor here who first thing you have is a thermometer. So you say, I'm not well. And then what you do is you generally check your temperature. And then there is a standard, you know, so like, you know, that when it is 97, you're okay. But if it is 99, you have a little bit of fever. And if it is 104, I'm sure that you will rush to the doctor. You know? So what you are doing is you're following a standard. Similarly, for vibration, if you see, we have something like a vibration meter. And with this vibration meter, you can take the reading of the vibration of a machine, and then you will compare it with some standard. It can be generally people use this ISO standard, and it can be also something which you have formulated from the manufacturer's data, or you can also arrive at your own standard. But you will compare it with something to know whether this is normal or this is in the alert zone or it is in the dangerous zone. So you will come to know about the severity of vibration. Then further on, what a doctor does is, once he knows that there is a temperature and there is a problem, maybe he needs to do further diagnosis. So maybe he uses a stethoscope to find out something more, or he will ask you to do an ECG or something. So this is what you do with the medical world. Now, in medical world, you have no choice. You know, I mean, you cannot say that, okay, chalo yaar, ek baar heart ko khul ke, let me just check it, whether it's okay or not, and otherwise I will close it back and put it back. You know, you don't do that. Whereas in machines, probably we could do that. However, why not employ this technology to find out, without stopping the machine, what is the condition of the machine. Does it need any kind of maintenance, or it does not need, or something? So in that case, we will also go for further analysis using maybe something like vibration analyzer, and then come to some kind of diagnosis with which you will then decide what further. So this is what we call as condition monitoring, monitoring the condition of the machine and then deciding what should we do. So some typical things, a doctor says that we measure the signals from the heart. A vibration engineer will say, okay, we measure the signals from the bearings. Or maybe doctor will order that, please take the blood sample with an empty stomach. And an engineer would say, okay, take the spectrum with so-and-so F max of 10 kilohertz, something like that. So primarily it is quite similar. So what a doctor does, similarly, a vibration engineer or a machine doctor will do this almost similar kind of steps. And that is how both are quite closely related. So now if you see, what are the different types of maintenance that we have? So corrective, or we can say breakdown maintenance. So here what you do is you allow the machine to run until it breaks down. You don't attend to it until it breaks down. Now, there can be some typical cases like this. For example, your fan at home, maybe it runs, you don't do any other maintenance, maybe except cleaning it. And then when it breaks down, you will see what to do about it. Or it can be preventive maintenance, which is quite popular. So at regular intervals, at regular periodicity, you will maintain this machine by, let's say, opening it, cleaning it, lubricating it, something like that. Or you may have very critical machines where you will say, okay, after so many hours of operation, I will change some parts and things like that. So this is all what we call as preventive maintenance. Then let's come to what is called as conditional maintenance. So now what you do is you observe the condition of the machine, various parameters, so you can observe the parameters. And then depending on how is the severity of this parameter which you're observing, you will decide whether to take it for maintenance or not. So this is what we call as predictive maintenance. Maybe you will plot something like this, which will give you an idea when it will reach the maintenance level, or when will it reach the breakdown level, and when will you have to do the maintenance. This is how, you have different types of maintenance. And it is not that, today the latest trend is predictive maintenance or conditional maintenance, so everything should be under condition monitoring. It cannot be practical. So what we really look at is that which machine, which maintenance, this is what we will have to look at. So I have a small kind of a flow charts here. So if you say that first thing is the machine breakdown a threat for production or security? So there can be some instances where, if the machine breaks down, your production is going to suffer severely, which is not affordable. And maybe there is a security kind of a risk. For example, let's say take a hospital. A tube light in a operation theater is so critical that if it fails, then there is a problem. Whereas a same tube light is put into, let's say, my home, okay, it fails, doesn't matter much. So we will have to look at such aspects. Then we say that is the cost of breakdown acceptable? If the cost is acceptable, okay, fine, go to corrective maintenance or breakdown maintenance. If it is not acceptable, or if it is a threat of production or security, then you check whether the monitoring technique is possible or not. If it is possible, well, go further. If it is not possible, then at least you can do preventive maintenance. Maybe you can, regularly maintain the system. And if the monitoring technique is possible, then can this technique be profitable? Is it going to cost too much, which I can afford it, or my system or my process can afford it? Then it's fine. Otherwise, I will go for preventive maintenance. And if it can be afforded, fine, I can go to prediction. Something like this. So you will have to find out which machine, which maintenance. And it may not be always true that in a particular company, all the machines will be under predictive maintenance. Within that, you will do what they call as criticality analysis. So whatever is a critical machine, you will take it up for predictive maintenance. And less criticals, you will go for preventive and maybe even corrective maintenance. So what you need to really look at is the cost and benefit analysis of predictive maintenance. So if you want to implement predictive maintenance, some of the capital costs you will have to spend. You will have to spend the money to buy the equipment, right equipment. You may have to train the people who can use this equipment, or you may have to recruit somebody who can use this kind of an equipment or make an analysis. You have to rework your maintenance procedures, etc., so that you can set up this complete program for predictive maintenance. The advantages which you will get, of course, are more time between shutdown. So you need not take a shutdown unless it is really necessary. No unexpected breakdowns. You can really almost find out that when the machine is likely to break. Less secondary damages to the machine. So supposing your machine is unbalanced and you keep running it, you are going to definitely damage your bearings also. So I mean, such monitoring can prevent some secondary damages. Better quality of maintenance, as well as better quality of life for the maintenance engineer. As you know, maintenance engineers are the guys who are always in tension. They are always wanted. Middle of the night, they can get a call to come back to the plant and attend to the machine. So such things, if implemented, at least their life can be much better. Right in time of spares inventory. If I can predict that 6 months down the line, this machine will need a particular bearing, which needs 2 months to procure, then maybe I'm better off and I can get the spares almost right in time. Then no wastage of spares. You are able to diagnose a problem and you will be able to repair it. So in the shortest possible time, you will be able to repair it, and you will probably not do trial and errors to repair the machine. So wastage of spares can be minimized. So these are the various benefits you can get out of this predictive maintenance. So this we have to weigh what is beneficial and how can we really implement this. So there are various monitoring techniques. So for example, you can process parameters you can monitor and do a predictive maintenance. For example, you can monitor the temperature, you can monitor pressure, flow, current, etc. And this can give you a good idea about what is the condition of your particular machine. Further, you have parameters like ferrograph or wear debris analysis, thermal imaging, and of course vibration monitoring, which we will of course talk more. So, for example, ferrograph, what it basically, or wear debris analysis, what you are doing is you are analyzing ferrous or whatever wear particles in the lubricating pipe. So just like a doctor takes your blood sample and tries to make an analysis of what is wrong with you, similarly, if you take the sample of lubricating oil from the machine, you will be able to find out those wear particles in it. And depending on the concentration of these particles, depending on the size and shape of these particles, it is possible to do a very early detection, or they call it as a detection of fault at the incipient stage. This can be done and a failure pattern can be established. And for example, very critical machines like an aircraft. In fact, aircraft would send their oil for analysis every some number of hours of operation, so that in case if there are any wear particles found, it can be easily detected at much early stage, and the right action can be taken. However, this technology is quite capital intensive, and it's not very easy to collect these samples and then put it for analysis, etc. There are some agencies who are available who are operating this as a business. What they do is they come and collect these samples from you from your company, and then they will give you the report of how is the machine operating, how is the condition of the machine. So these are possible. Then thermography is another tool. Here, basically, what you do is analyze the temperature profile. So, like what you see in this picture on this slide, you can see that there are some red spots of the bus bar which is connected there, and this means that that particular spot is heated up, and the reason for this heating can be found out. So it is possible to do such thermal image, and you can find out the condition of your machine. For example, in a cement plant, you see those rotating kilns, which is a very high temperature inside, and then it is lined up with those refractory lining. In case if these refractory linings are worn out, then what you can see is those hot spots, which can be really identified easily with this thermography kind of an instrument. And then you can do the maintenance, required maintenance. And this can be very useful for predictive maintenance. Again, this is also capital intensive. Nowadays, of course, some cheaper solutions, cheaper equipment are also available. And yeah, it's not very suitable for mechanical damages, especially in the early stages. Vibration monitoring, the topic of today. So vibration monitoring has been quite a popular tool to do the predictive maintenance or predict the machine condition. The main features of this is that it is easy to collect, very early detection it can provide. It is a failure signature, so you can make kind of comparison of different signatures from different times, different machines. It's quite a suitable tool for alarm monitoring, predictive maintenance, and diagnosis. We'll look at these details a little bit ahead further. So this is what makes vibration monitoring quite popular. In most of the process industries, you will find them in many industries. So though there are many types of, I would say, measurements done within vibration monitoring, two most popular ones is something which I will be talking about today, and we will see here. There are many of them which, as I told you, that over the period as we are going to have more and more such seminars, webinars, we will definitely be able to discuss them later. Today, what we are going to talk about is this overall measurement and then frequency spectrum. So overall measurement is primarily one value. So if you have one value, which is vibration amplitude or something like a temperature of the body, which you say, okay, this is a value, compare it with some standard, and you know whether this is okay or alert or danger or whatever. So you can monitor a single value, and the result is very easy to use, suitable for monitoring, and but it is generally inadequate for diagnosis. Like a thermometer cannot tell you whether the temperature is because of COVID or because of viral or because of something else. So this we need further tools to do the diagnosis. Similarly, in vibration, the further tool very commonly employed is frequency analysis. It's also called as FFT or fast Fourier transform or a spectrum. Primarily, it is a plot of amplitude versus frequency, and it has more sophisticated result, and it allows you to do the diagnosis of what is wrong with you. So there are many other parameters, as I told you, like time of room analysis, capstone analysis, orbit analysis, transient, array plot, impact testing, cross correlation, cross spectrum, envelope, things like that. So all these are there. Many of them are very useful, can be doing a lot of detailed analysis of the machine. But at this moment, we will not be talking about all this today. Maybe at a later date, yes, this can be also one of the topic which can be talked about. The subject is quite vast. In fact, Dr. Pine was telling me that he wants to do one session only on units of vibration, only on units of vibration. So it can be even talked so much in details. So today what we are going to do is, okay, touch upon everything that that is there, and then just have an awareness of this. So what we call as amplitude. So what is amplitude? So if you take a vibration waveform, it is kind of a, it will not be, of course, as simple as this, like a sine wave, but it will be multiple of sine, multiple summation of sine waves. So, but if you say a waveform, a repetitive waveform, what you have is an amplitude, which means how big is this? Is amplitude. So if you see on the left-hand side, you have a waveform which is a higher amplitude, which is in red, and the one which is in blue is a lower amplitude. And then for a waveform, we normally define a peak, like you see on the right-hand side in the you have what we call as a peak value. So that means from the 0 to maximum is peak. And then between two peaks, whatever is there is called as peak to peak. And then, of course, there is an RMS value and an average value. So these are the different vibration amplitudes which can be defined, which can be seen. And then vibration is primarily a motion. So all laws of motion apply. And even parameters that you monitor for motion is same parameters which you will have for vibration. So you have displacement, as I've shown here on the right hand side. You will see that, okay, there is this suspended mass which will oscillate here and which will generate a displacement. You can visualize. So there is a displacement of vibration which is denoted by x. Then moment you have a displacement, you will have velocity for that. So velocity is rate of change of displacement. So you will have velocity, and then you can have rate of change of velocity is what we call as acceleration. Or if you mathematically, you can say double differentiation of displacement will give you acceleration. Okay, so this is how they are interrelated between three of them, displacement, velocity, and acceleration. And you can monitor them for whatever parameters you want to know. So this is all we talk about as vibration amplitude. Now, once you monitor vibration, you need to compare whether this is like what you see here in green zone or in the yellow or orange zone or in the red zone. Now, human body is same. So we have a standard for human body. As I told you, the temperature is, let's say, 97 is okay, and 99 is alert, and then maybe 102 is danger, and you have to rush to a doctor. However, in machines, what happens is there are different sizes of machines. So not the same values will apply for every machine that is there. So you have to look at it in a different way. And this standard like ISO 10816 divides this machine into 4 different classes. They call it as class 1, class 2, class 3, and class 4. My next slide, I will show you what are they. And then depending on which class of machine you are monitoring, what is the value of vibration velocity? And then you can say whether this is in acceptable range or it is in unacceptable range, or something like that. And then so these different class of machine, what you have is these are all the rotating machines from 600 to 12,000 RPM. This is applicable for that. And the measurements are done between 10 Hertz to 1000 Hertz of frequency. That is the vibration meter which you will use will have this kind of a frequency range to which it will respond. And for class 1 machine, basically small machines up to 15 kilowatt of power. Class 2 are medium-sized machines which are between 15 to 75 kilowatt. Class 3 are large prime movers which are mounted on heavy or rigid foundation. And class 4 are on the relatively soft and lightweight structure mounted prime. So this is how they have classified this into 4 different classes. Now, when should I measure? How often should I measure? So periodic measurement is something which you will do. So you, depending on the criticality of the machine, you will decide how frequently you would like to monitor this machine. So you can take the readings on those periodic basis. However, if the last time you measured and this time you measured and there is a significant change in the value, then it is advised that you take more. You take the readings more frequent, and then you define what is the trend of this vibration. So when you plot it in a simple way, you will see something like this, which is called as a trend. You plot all these values, and then you can extrapolate this curve to find out what is the alert level and the breakdown level. And if you look at this, the way it is progressing, you will be able to predict that at what date you are likely to reach the alert level, and probably at what date you will be probably reaching the breakdown level. So this is the time when you prepare between alert and the breakdown level. You have the time to prepare for your maintenance. That means you can order the spare parts, you can plan a shutdown, and then you will be able to shut down the machine at the right time to repair it or maintain it. Okay, so this is what is called as trend analysis. Now, so we talked about amplitude. Now, the second parameter that we are going to talk about is frequency. In general, what is a frequency? Frequency is rate of occurrence of an event is frequency. So we say, okay, my bus comes every hour, so that's a frequency. Similarly, in vibration, we will say, okay, this waveform repeats at what what times it repeats in particular time sequence. So it is called as frequency of that vibration. So different vibration defects produces different frequencies. That also we'll see in detail. So this is what we are going to use to find out that what is the defect in a particular machine. If you look at the waveform, so I've taken an example of sine waves. So if you see the top one, it shows a particular way, and then if you see the time for one cycle for the waveform which is in red as compared to the waveform which is in green, the time for the red one is larger time, and time for the green one is the shorter time. That means this is the difference between the two waveforms. And if you divide the time for, I mean, if you take the inverse of time, which is 1 over t, will give you frequency. So if you see here, the frequency of waveform 1 or red waveform is lower than the frequency of the lower waveform or the waveform 2. So this is how different frequencies are measured, or different frequencies are generated by different machines or different components of machines, I would say, which can be identified, and you can make an analysis. So if you plot that, if you take the value of each waveform and plot that on a scale which is frequency versus amplitude, you will get something like this waveform, which we call it as a spectrum. So primarily what is done is, in a complex waveform, if you see the waveform here, right here, it's kind of a practical waveform which you will see from a machine. This is a complex waveform. So this can be divided into series of sine waves. This is what Fourier's transform says. So Fourier transform says that any complicated or any repetitive waveform can be divided into series of sine waves. So here, what example I've shown is maybe this T1, T2, and T3. These are the three waveforms. If you add them together, probably you are going to get what is shown at the top. So this can be splitted out by using the Fourier transform into different frequency components, like what is shown here. And then this can be plotted in the way it is plotted in the top one, that is amplitude versus frequency. You will get what is called as a frequency spectrum. So for example, something like this, if you have a machine, you have a motor, so you may have, the lower region, medium region, and the high region of the vibration frequencies. So some components like gears or bearings will generate, higher frequencies. The couplings or something will generate in the lower region. So, this kind of a thing you will see, and different kinematics of these machines will generate different levels of vibration. Different frequencies of vibration, and depending on the severity of that particular problem, the amplitude of that particular peak will be higher or lower, depending on what is the problem, on how severe is the problem. So this is how you will get a picture of condition of the machine, from which you can analyze and you can come to a conclusion of what is the present condition of this particular machine. So if you see different types of faults, I've just listed down whatever I could remember. And if you can see that, like for example, unbalance, which is quite a popular, or quite frequently you will find unbalance in the rotating machine. So this will occur at 1 times the rotor speed. If my motor is rotating at 3000 RPM, or 3000 RPM is 50 hertz, 50 cycles per second. So the frequency which you will see because of unbalance will be at 1 time the RPM. That means it will be at 50 hertz if the motor is rotating at 3000. So 1 time the rotor speed. The predominant direction in which it will be present, it will be radial direction. So if you see a machine or a motor, you have 3 directions. You have x-axis, y-axis, both are referred as radial direction. And there is also an axial direction. So there is Z. So these are the 3 directions. So predominantly in radial direction, you will see an unbalanced value. If it was bent shaft, well, you will see 1 into RPM, but it will be also sometimes 2 into RPM, but predominantly in axial direction. So such things, if you see various probable cause of vibration can be seen in this kind of a table, and you have various possibilities wherein you can try to find out what is this defect frequency and what is the amplitude of this defect frequency, and try to find out what is the problem with your machine. So various things like defective bearings, mechanical looseness, or there can be operation parameters like blade or rain pass frequency from a pump, agitation, or problems with the drive belts. So various types of problems can be identified with different frequencies, like oil valve or gear problems. They can be all identified. So what is essentially is required is that with your machine, you will have to first find out what are the defect frequencies this machine will generate, and then monitor that and see how these frequencies are increasing, or these frequency components are increasing, and accordingly you can come to know what is the issue with your machine. So I hope this was quite clear, or you would like to have some questions before we go further? Should we?
You have not talked of the roller element bearings also here, sir? You have talked only on.
Yeah, even roller element bearings, maybe defective bearing, anti-friction bearing, which is your roller bearing.
Yeah. So there, where you will have both bearing to bearing defect, or bearing to inner wall, or bearing to outer wall.
Yes. You in fact you can you get 4 frequencies which you can identify. That means inner. I mean the ball pass frequency, the inner cage, outer cage. I mean rather the cage frequency, inner and outer race. All 4 frequencies can be identified. In fact, it can be seen on the spectrum also.
Yes, yes. Either in an envelope analysis, it is brought out very clearly.
Further on, see, basically what happens is why you do envelope analysis or something is, this spectrum which you see sometimes looks very complicated because it has so many frequencies. And you are trying to then apply certain filters to see that you look at because, if you have the low frequency and high frequency together in any place, there is going to be a tendency of a modulation. And to remove this tendency, or to filter this out, you will do something like envelope analysis, with which you will be able to see those frequencies more clearly. The defect frequencies can be seen more clearly. Okay. Any other questions now, or should I go further?
Sir, I have one more question. Yeah.
Sure.
Sir, when we take the realistic spectrum analysis from the realistic signals, time domain signals to spectrum, many times what will happen is what we eradicate, saying like misalignment, unbalance, all these things will club together. How do you eradicate those type of things or remove one by one correctly? Say like one time 1x will come either for the unbalance or for misalignment, even for rubbing.
Yeah.
Is there any easy method to identify this?
Yeah. So primarily, see, once you know what are the expected frequencies. So, for example, as you say, that there is unbalance, and I got a 1 into RPM. Also, I get a 1 into RPM peak with bend shaft, for example. Right. However, if you see the direction, in case of unbalance, it is predominantly in the radial direction. If you see, let's say, misalignment, then misalignment, you will find that misalignment is generally, yes, again, 1 into RPM, but you may have other harmonics, 2 into RPM, 3 into RPM. And alignment will also have, if you have any kind of angular alignment or something, a misalignment, then you will also have the axial component. So you will have radial as well as axial components. So such combinations will have to be seen on the spectrum, and then you will be able to come to a conclusion that yes, what is the problem in this machine.
Mr. Mukesh, could you go one slide back, because I think that is what so that is where he was asking, bent eccentric. Yes.
True. No, when we take the real signal, everything will get mixed together. It's very difficult to identify whether it is because of unbalance, bent shaft, misalignment, or eccentricity, or even rubbing or whirling, all these things. Any easy method to identify that? This is what I want to know.
Frankly speaking, see, what you need to know is what are the expected frequencies. As you said that, let's say 1 into RPM, I can have one peak, which is at 1 into RPM, which can be unbalanced, or it can be also because of, let's say, bend shaft. Let me say within this slide, if I say, okay, bend shaft also gives me 1 into RPM. However, look at the direction. So if you take the reading in radial direction, and if you see that the 1x is a high component, and then if you take the reading in axial direction, if that component falls down, that means it is definitely unbalanced.
May I come in?
Yeah, fine, sir. You can come in. You are more practical guy.
Actually, see, any signature is coming from the machine or is capturing from the machine, and by any means we have to identify each type of problem separately. That is the importance of the vibration, and we have to do it, and we'll get it. Here we have to take another phase analysis, uh, phase analysis that will determine our unbalance, misalignment, and cross coupling in information is something misaligned or something different resonance of the structure, or if some loading on the pipe loading is coming on the machine. All things can be separate out by phase analysis. Besides that, you are analyzing this entire spectrum over the time. By this time you have a feel about it, and you have a good monitoring setup like online monitoring setup on that machine. Then you get extra orbit of the machine, orbit of that particular from that particular bearing will orbit of made out of horizontal or vertical vibration, or any position you get a 90-degree angle, if sensors are placed, you will get an orbit. That orbit can be captured either in casing or normally conventional, whatever you are getting from eddy current probe. Both way, orbit shape will determine. Suppose it's misalignment, it will be completely flat, okay? Or if it is elliptical, good enough for a good machine. It all machine almost running on that pattern. We will never get orbit of circular in any journal bearing machinery. So all its defects are whether eccentric air, bend shape, unbalance. There is one time RPM has got so many other applications besides its direction. So you will get by phase analysis, you have online system, you have on orbit analysis, you have many other options are available. If more you invest on the vibration monitoring system, you will get the how to best you can separate out, you will get the systems in your software or your instrumentation. It's possible, definitely possible. Otherwise vibration analysis won't be fruitful and we will not get best out of it.
Thank you, sir.
Yes, sir.
So for the eccentric motor, if you start looking, for example, in India at the 50 hertz lines, so then you are looking at very clearly 50, 100, 150, the mains and the side bands coming up. And also, the moment when you switch off the power, then the electrically induced vibrations also immediately tend to vanish. The mechanical vibrations remain, but anything electrically induced will go off.
Yes.
Yeah. So, for example, if there is electrically induced vibration, and if you moment you switch off the machine, that will vanish.
Yes. So
It
that
can
is
be
when you are looking at frequencies which are at your power frequency. So in India at 50 hertz.
in
So
fact, it can be done with a very simple vibration meter. If you have those analog meters, that is the ideal tool to find out whether it is electrical fault or a mechanical fault. So, there are various possibilities. There will be a lot of practical aspects also to this, and then of course the technology. So you have many parameters which you can monitor and try to identify finally what is the machine. And as Dr. Pine said, he has a lot of practical experience in steel plant and the refineries where you have almost every type of machine. And yeah, very complex analysis can also be done, and you can arrive at those. So thank you very much, Dr. Pine, for highlighting those details.
I think also Mr. Madhusudan had given a lot of points.
Right. Correct.
Yes, Madhusudan has given phase analysis. Yeah, right. Exactly. We will get the pinpoint the problem definitely.
Yes.
Okay, sir. Please go ahead.
Right, sir. So now let's quickly look at what is a vibration analyzer. So how does it look like or whatever. So I just try to, in a very simple block diagram. You have some kind of a sensor. You have some kind of electronic box, which you will do the processing. And then further on, of course, you will connect it to your PC or a printer and things like that. So generally, it will look like this. So you have an machine to which you will mount the pickup. We call it as an accelerometer. I'll also describe a little bit about those pickups. And then you have an analyzer to which you will connect this pickup and see on the screen some kind of a waveform. It can be time waveform, which can be frequency spectrum, and things like that. So traditionally, the first one, maybe many of you would have used this also. There used to be a displacement pickup. It used to be a massive, size of a pickup, wherein there used to be a magnet suspended inside a coil, and then as you see this, moment you have a vibration, this magnet will move inside the coil, which will generate the voltage, which is proportional to the vibration displacement. That's how this was designed as a vibration pickup. However, it had various problems because it was very bulky. It needed very frequent calibration because there was real physically moving thing with this magnet. However, this used to be the up in the beginning. Subsequently, of course, a lot of developments took place, and what you would see now, and of course for many years now, you will see something which is called as the accelerometer. So here, what is done is the piezoelectric crystals are used. One of the typical configuration will have very, if you subject the piezoelectric crystal to some kind of a force, it will generate an electrical charge, or I would say electrical output. So, which is proportionate to this particular force which it is subjected to. So here we subject it to vibration, and what you will see is that proportionate electrical output is available, and this is proportional to acceleration of vibration. That's why the name accelerometer. And as we saw earlier, that if you have acceleration measured, then you can always convert it into velocity or in displacement by integrator. So if you have acceleration, if you integrate that, you get velocity, and if you double integrate that, you get displacement. So this is very, very popular pickup because it is available in various sizes and shapes. It can be very small to the kind of things which you are seeing on the screen now. Primarily, it will have a charge output, but with certain accelerometers, which is very practically used in most of the portable equipment, they have a built-in amplifier in it, and it gives you finally the millivolt output, and it is referred as its sensitivity is referred as millivolt per G. G is the acceleration of vibration. So you can have an accelerometer and connect it to an analyzer, a handheld analyzer like this, and there will be an interconnection cable. Now, depending on how you mount your pickup, also have some effect on the way you get the reading, or you see the reading, or you can say that there will be a useful range of a particular pickup. So, for example, the same pickup, if I hold it by hand by using a contact point, then the resonating frequency is at around 2 kilohertz. That means I can use this pickup only below 2 kilohertz, maybe around 1 kilohertz or so. With the same pickup, if I use a magnet mount, then this resonating frequency shifts to almost about 7 kilohertz. That means my useful range of the pickup is increased. And if I really cement this pickup by using a cementing star, then what I get is a very useful range, which is quite large in frequency. So useful range of the same pickup can increase depending on the type of mounting you use. Of course, the best is cementing it, but then it takes more time. So depending on the type of measurement you're doing, most of the time you will use the magnet, which is quite sufficient. And in some cases, you will also use the handheld version, so which is fastest.
Why do you call it a cementing stud? I mean, a standard stud is the same. There's no difference between a normal
Yeah,
stud and a cementing stud.
cementing stud is just to say that you will cement it, or you will fix it maybe using some adhesive or something.
No,
Very typically.
the adhesive will melt at low temperature. So what we are, my perception is that you actually tap the surface and put a 1032 or M3 stud permanently into the structure.
Yeah. So normally, there are two ways of doing this permanent mounting. What you do is either you drill a hole in the machine with providing those, threading, and then you will, screw the pickup permanently, or maybe the stud is permanently there, and every time you go there, you will screw it up on that.
Yes.
The other way around was to use a stud, and you fix the stud permanently on that, so you don't have to do any work on the machine. And then on the stud, you fix up your accelerometer. In fact, in 01 dB, they used to have this as a standard item available, which was called a cementing stud, which are small aluminum discs available, which you can stick it onto the machine, and then on that disc you can screw your pickup whenever you take the reading.
You can also use, I mean, we have used wax for
Yeah,
measurements.
beeswax.
We could use double-sided tape.
Yes, very true. So beeswax was quite popular.
Beeswax is still used. The problem
Okay.
is, let us see, on a table or something for demonstration, you could use it.
Right.
However, because it melts up to 40-45 degrees, so you cannot
Yeah.
use it for a machine.
Right. In fact, I once time long back, I was called for a monitoring of the jet engine starter. And for this jet engine starter, they told me that you have to take the reading, of course, inside their test room. Before they put it onto the aircraft, this is to be tested. So I went there in Air India, and then I did not realize this, that the speed at which it starts, I mean, from 0 to maximum RPM, it takes hardly any time, and there is so much of a pressure drop in that cabin. So I was holding this because it's an aluminium body, machine. So there was no magnet possible or nothing. So I was just holding it by hand, and it was just a trial demo. I mean, within no time, my hand started freezing because of the pressure drop. So yeah, we have to use some specific type of adhesives or something to take such reading.
Yeah, normally in the aerospace industry, they would prefer either a magnet or a stud because the frequencies are so high, you just cannot. And as you correctly put it, in your hand, maybe even 200, 300 hertz later, your hand acts as a high pass filter.
Yeah.
In my experience in XL and all, they use studs only,
Okay.
permanently mounted. And if it is on the test bed, as you said correctly, there are already either studs or holes fixed. So you just fix the accelerometer there, and then it's fit and forget for the rest of its life.
Perfect. Yeah, and even you said about the temperature, because many
Yeah.
times the temperature
Yes,
is so
yes.
high, and
In gas turbines, in aerospace industries, the temperatures typically are around 350 to 400 degrees centigrade. So you will have to use only charge accelerometers. ICP accelerometers do not work above 80 degrees centigrade.
too high. Okay. So yeah, this was then other type of pickup which is very popularly used with the journal bearing monitoring machine. I mean, journal bearing machines monitoring. These are proximity probe. So this proximity probe primarily detects two things. It detects the gap and the relative vibration. That means it will monitor the shaft, and as the shaft vibrates, the distance between this pickup which has been mounted and the shaft varies, which gives you the relative vibration. So accelerometer is an absolute vibration, whereas proximity is a relative vibration. So mostly all the journal bearings machine will be using the proximity probes for monitoring vibration. Now, different types of different monitoring points. So, for example, if it is accelerometer based, what you see in yellow here, these are the accelerometer mounting points. So RV is radial vertical, RH is radial horizontal, And here, what you say 1A here is the axial direction. This is how accelerometers are mounted on the machine casing, and then you can take it. And if it is a proximity probe, then you have to, of course, pre-install these proximity probes. These are done by drilling the holes, and then you're fixing those probes there and adjusting, and you have to calibrate this because the gap is what is going to be monitored, and it is relative vibration. So for relative vibration, you will have to first calibrate this, and then you will be able to monitor. Is another view how your machine and let's say motor coupled to machine is looked at, and these are the different points at which you can monitor vibration, like axial, horizontal, and vertical. Yeah. Some typical block diagram for somebody who's interested from the instrumentation side. We normally have a preamplifier to which the pickup is connected. There will be some kind of a filter so that you can filter out certain frequencies which you don't want. It can be kind of a bandpass filter. There can be an integrator. If you have an accelerometer, you may want velocity or you may want displacement. Accordingly, the integrator or double integration can. Most of the meters that you see are all digital meters these days. So you will have some kind of an A to D converter, and then finally a display. This display, you can see the reading which are being measured. And then a little bit more complex, of course, again, simplified in this block diagram is your analyzer. Here, after the conversion of the signal into digital, what you do is you have a processor. We call it as digital signal processors or mathematical processors. So with this, you will have more complex functions done like FFT and whatever, and then you will be able to display those things on your graphic display. Of course, you will have memories, you will have communication to the PC, and all kind of things can be in the same equipment. So normally when you want to buy an equipment, there are certain key parameters which you should look at. For example, the dynamic range of measurement. Basically, what dynamic range means is that within the same screen, what can I see as the lowest and the highest value? How can I, see it in the same screen? So depending on the dynamic range of the equipment, you will be able to same screen. Otherwise, you may have to, choose to look at the lower value in a different resolution and a higher value in a different resolution. So this dynamic range is generally defined by the A to D converter's resolution, which is, let's say, if I say I have a 4-bit A to D converter, then my resolution is 1. But if I have, higher bits of A to D converter, like 16-bit or 32-bit, then my dynamic range will be definitely much better. Then another thing you have to look at is the frequency range of measurement. Depending on your application, you will have to see that what frequency range will be suitable for you. Of course, most of the equipment will have a sufficiently large frequency range. So it can do both the things for you, the lower frequencies as well as the higher frequencies. Frequency resolution is another important parameter. So how are you going to see them on the screen? For example, if I have a 100 hertz waveform, and if I have an analyzer which is 100 lines, that means the resolution which I will get is 1 hertz per line. That means if I have a reading which is at 1 hertz, I will see that, and the next one I will see it as 2 hertz. And the same 100 cycles, if I see it with 400 line resolution, then I will have 0.25 hertz as my resolution. So depending on your application, again, you can look at what is the resolution you should have. If I'm not wrong, currently you can find the analyzers which are even something like 12,800 lines resolution, even more. And then other parameters which you will need for analysis. So you may need various parameters like time domain analysis. You may want orbit analysis. You may want dual channel analysis, spectrum, cross spectrum, and things like that. Envelope spectrum. So most of this equipment which are available in the market today should be able to give you all this kind of parameters, and you can use them to do the detailed analysis of your machine. Of course, portability. If it's a portable equipment, you would like to look at how portable it is to carry around, because most of the times what condition monitoring engineer will have to do is go around into the plant to collect the data. And then if it's a portable equipment, it is really easy to do that. If it's an online equipment, you have to look at the response times. For example, if it's a vibration online monitor like what you see with Bentley Nevada or something, where it has to shut down the machine in case of a problem. So how is the response time, which is defined by this API standard, and then that has to be looked in. The memory capacity, depending on how, like I know typically like a refinery, I think they have to collect a lot of data, a lot of machines. So if you go on one round, if you're able to collect more number of machines, maybe it will be better. So you may need a higher memory capacity. Further down, the software for analysis, you can have some diagnostic software built in the equipment itself, which can probably do some kind of a preliminary analysis. So with quite a bit of good confidence level, for example, it can tell you that this is because of unbalance, or this is unbalanced with confidence of, let's say, 80%, 90%. This software can tell you. You can also have this further detailed analysis by these diagnostic software on the PC. You can also have some other techniques built into the same equipment, which is also useful when you are doing this kind of monitoring. It can be, non-contact temperature measurement, built-in non-contact kind of tachometer, built-in camera for taking some pictures, like if you have any oil spill or something like that, which you would like to have it for your detailed analysis. And then you also, of course, would like to know about the support available from the vendor, like calibration. I mean, there are a lot of equipment available, but many a times you don't have the right place to go for calibration. Calibration is essential. Any measurement equipment, you definitely have to calibrate them at periodic calibration, maintenance, and then of course application support, etc. These are the points which So I think this is what I thought I would touch upon for this today's topic. Any further questions?
I think another point that would be considered, because we have the friends from our petrochemical industry, one of the important things in an analyzer would be whether it is can be used in intrinsically safe areas. I mean, that's a
It's
major
really important, very, very important, because if it is not intrinsically safe, then you should not, or you are not allowed to use it in the atmosphere, which is hazardous area.
Yes. Another one is also, I would say, go back to the sensors, because today, for example, if I'm using in a nuclear power plant, then I would have to use nuclear hardened sensors.
That also, yes, very true.
So right from sensor range, sensor temperature, all environmental conditions, charge versus ICP accelerometers, which is a constant thing, because you cannot use ICP accelerometers above 180 degrees. Charge accelerometers, most charge accelerometers work only to 230 degrees. So for gas turbines, then there is a special 480 degrees accelerometers. Of course, cables also. Cables are very, very expensive. So in a high temperature accelerometer, with my experience, high temperature cable is almost 10 times the cost of a normal cable.
Right.
So you will have to take multiple cables. So you have some stainless steel cable for the hot zone, then take normal cable for the cold zone. Otherwise, the price of the cable is going to be 10 times the cost of your system.
Right.
These are some points. Calibration, of course, is, as you said, most important. ISO 160-163 talks on sensor calibration, which a number of labs in India can do that, no problem.
Right.
So whether NPL or ARAI, CRI, these are three of the standard labs in India which do sensor calibration as per ABL standards.
Any other questions, gentlemen?
Any other question?
Yeah, I'm Sundar here. Am I audible?
Yes, yes.
Yes, I don't this vibration switches. Okay, with this sensors we have seen and how they are being effectively used. But when it comes to vibration switches, how are they of course, we know the functionality, but in terms of the selection or in terms of the accuracy of their response, any thoughts on that?
Frankly speaking, I don't have much experience on vibration switches or use of vibration. What I know is that it also has the same kind of a similar kind of a sensor and a contact. Moment it vibration grows above the certain limits, it'll actuate that contact to shut down your machine or take some action. Anybody can come on this if you have any ideas about using this kind of switches.
I mean, I just my contention is just like a pressure or temperature switch, purely a protection mechanism.
Rajshekhar, your voice is breaking, I think.
Yeah. So, okay. From my experience, these are purely like an alarm and trip system. That's all.
Yes,
Yeah.
yes.
So,
Sundar Saab, yes, Sundar Saab, correct. You are very right. This is just an alarm and just one time you get alarm and over there is some problem in the machine. Neither you can get data, nor you can analyze, neither you can transfer to any other instruments. We had number of things in our cooling tower fans. They put it nowadays you don't find it except old plants and other places. You won't find anywhere vibration switch.
Yeah, in earlier the protection was more on the vibration switches for the appropriate equipment. Only thing is we just used to leave it as it is, but how they are calibrated or even what is the confidence level we have in their functionality that it will do its job at the right time.
Yes.
And in terms of their design, are they different from these?
Mechanical, just electromechanical. That's all.
Okay.
they're purely electromechanical. They have a relatively low frequency, and they will be like what Mr. Mukesh put out, something like the ISO 10816, just an overall vibration level.
Yeah. Okay.
So your machine may trip, but it need not necessarily protect because vibration frequencies are developing at the lower ones, but it could be hidden at an overall. You might get an alarm very late also with these switches. So you have to be careful.
Before
Can I add, Mr. Mukesh?
Yeah, sure.
Yeah, just this vibration switches are basically a safety device to energize a NONC contact. There are two types of switches, mechanical and electronic switches. So these are mostly used for the cooling towers. So cooling towers basically because you can energize the contact and trip the cooling tower motor based on the imbalance of the fan. So imbalance of the fan, they just energize the contact and give a trip signal. So as far as the calibration of the switches are concerned, that is a voluminous weigh device. For example, there is having 800 grams, and using the same the lab, just the mounting device has to be different to mount on the shaker, the switches, and that can be calibrated just like a vibration transmitter. You can say it is a vibration transmitter which can give a NONC contact output and trip the equipment, whether it is cooling tower or any other industrial fan.
Yeah. Okay. And just one more general question out of my curiosity. This pure vibration sensors, vis-a-vis, now the combination, we know that vibration come temperature, or you also mentioned about another one or two parameters.
When you go for that more than one functionality apart from the main vibration, is there any compromise in the main vibration way it is done?
So frankly speaking, what happens is it is really speaking, it's not one sensor doing both the functions. It's a separate, like for example, accelerometer is connected to the only thing is within the same electronic box, you have 2-3 different things put together. So for example, if you have a temperature, there is a thermopile sensor inside for temperature measurement, non-contact temperature measurement, and this will measure the temperature. Now what happens is you collect this data. So you are at the machine, you are collecting the vibration. At the same time, you're also having the same equipment with temperature sensor inside. Then you can also take the vibration, temperature reading. There is no compromise. There is no other compromise.
The ideal thing would be to have personally two separate sensors, because the mounting of the accelerometers is very important and the mounting of the temperature sensors is equally important, but may not be in the correct place where the accelerometer is mounted.
I'm talking about this non-contact temperature sensor built into this equipment, so that you can get a quick reading of that temperature.
Yes, but combining this in sensors is personally not.
Not in the sensor, really. It's not in the sensor. It is in the equipment, the analyzer.
I mean, today you have in the motors even thermistors which trip if temperature goes high. Most variable frequency, most motors today have a temperature protection system, an RTD inside or a thermistor inside.
Right. So even some of these equipment have, let's say, for example, a camera inside, and this camera is a standard camera. The idea is that when you are taking some reading and you find that you saw some let's say oil spillage near that particular machine, and you just want to quickly check it out. I mean, you want to just quickly note it down, or you want to take a picture of that. So within the same equipment or same box, you are able to do that, and then use it for your data monitoring or your let's say collection of the information or generating the report and things like that. Or for example, tachometer, of course, it is necessary when you use the same equipment to do balancing or to
interested in both in balancing as well as order analysis, waterfall plots everywhere. You will require at least one tacho signal. In case of gas turbines today, you also have two tachos because they want to measure vibration with respect to tacho 1 and respect to tacho 2 especially in aero gas turbines. I just did this measurement 2 weeks back also. So on and on.
Just to add to Mr. Mukesh and Mr. Rajesh, basically, vibration accelerometer with a thermistor, inbuilt into that, that is used to measure the bearing vibration plus bearing surface temperature. So that is handy in case of motor when there is some background noise. Okay, so basically that is used for measuring the bearing surface temperature as well as the bearing vibration. So that proves handy in those situations where you have the bearing vibration plus surface temperature both at the same time. You can use using the same sensor. There is no compromise. There are two outputs independently where with a 4-pin output connector instead of a 2-pin output connector for a normal accelerometer. Two pin will be for vibration, 2 pin will be for the thermistor output. So independently to each other, there is no compromise as such.
Okay. Thank you.
Thank you very much.
May I request all to show their face? We can take some screenshot while question answer is going on. No problem.
Should I stop sharing the screen to get the?
Yes, please. That's why I was struggling since long. You please stop share. Yes.
Now we will see everybody.
Yes. Everybody, please show your face. We take a screenshot just for our record, nothing else. Yeah. And someone there, please take screenshot. Gupta ji or Uchil Saab, koi mera idhar kuch problem hai machine mein.
I'm doing it.
Yes. Somebody then later on share. Kopkar Saab, thank you very much. Then, okay. I think some of them already left. Even then, just for our record. Karanji, Dipayan or Saksidas, Srinivas, Bhagu sir, show your face, everybody. And you take a screenshot while question session is going on, no problem. Yes, after that, yeah, that looks nice. Yes, Sundar Saab smiling, very nice. Take some.
Thank you, sir. Thank you.
Thank you very much. Okay, carry on now. With this, I want to add on with the advancement of so much technology and vibration monitoring system and vibration analysis features inbuilt in the instrument as well as software. People are very smart. They are least bothered about their switches. They are when to throw this switch, when you are taking out these instruments from here, because then people are so much hungry that they are not happy with the overall one parameter vibration limit. They are now very detailed analysis of vibration. World has changed now last decade. So I think vibration switch, you have to throw it out wherever it is there. There are so many other safety things are available right now, sir. You are from top much company. We should encourage them to buy the best instrumentation.
Sir, Mukesh sir, I have one question. I'm Lokesh here.
Yes, sir. Professor Saab, boliye.
Yeah. Sir, usually, generally we say, Usually, generally we say when we were telling the audience that FFT analysis has got a drawback, that it is suitable for a stationary signal. And the major drawback of that FFT, we say that it is not suitable for non-stationary signals. That's why we went from time domain analysis, frequency domain analysis to time frequency analysis. Can you throw more light onto this?
Moment we say FFT, see, Fourier transform is applicable only if it is a repetitive signal.
But then today, when we are doing, sir, if you are doing order analysis, for example, in real time or waterfall, then you are looking at it in real time, frequency and speed. So there is not a problem at all. Most advanced analyzers show you in real time with very good deterministic values. So
Yes.
you could have the time signal and you could have the frequency signal even at as high. I mean, yesterday I ran signals at 10 kilohertz, absolutely no problem, real time.
My question was because of the, say, like, if there is any one small flaw in a rotating gear, let us say,
Yes.
that will definitely not give the stationary signal. It definitely give a non-stationary signal. Then how the FFT analysis will help us in such type of thing, because that teeth which is having a contact may come not continuously. It may come very oftenly whenever it is in contact with the another unhealthy teeth. That's the reason I'm asking this
Yeah.
question.
So when you have periodic gearbox signals or belt signals are normally periodic, but which are hidden in the aperiodicity. So in which case, if you use techniques like strum or envelope, you can pull out these components.
Lokesh sir, may I come in? Lokesh sir,
Yes, sir. Please, sir.
Actually, we all are talking on a dynamic signal, and vibration is dynamic. Anything coming continuously or running state is of our study interest and our vibration interest, instrumentation interest. So static signal and dynamic signal, I'm not getting you, sir. What is actually your doubt?
No. My doubt is non-stationary signals. Say like a non-stationary signal is if in the beginning of the problem creation, generally there will be a non-stationary signals that will go within short time. But FFT is applicable for a stationary signal where it continuously. But our duty is to identify the fault when it is in the incipient state. For that, definitely it gives a non-stationary signal. To identify such a small time duration variation, how far it will be benefit and what is the best technique to identify?
Normally, in a run up or run down, you could be able to identify such transients also.
Sir, there is an issue when you are starting a machine. We get transient signal. That's what
Yes.
I mean for a transient analysis.
Yes.
So while starting up and coasting down, we get a signal and we analyze totally separate thing. Okay. And in case of FFT, you start the machine is running, whether it is very small value in stationary state almost, or it is very high amplitude value is your least concern, it will pick up everything. It is our concern what amplitude, what frequencies machine is running. We will get everything in FFT. FFT is nothing but all about transform form of amplitude wave domains, and wave domain when it will come when there is some vibration motion. If there is some vibration motion, then only we are measuring. And if there is stationary, it is not our importance at all to study. I'm not getting. That's why I'm telling you, sir.
One thing I want to add here, for example, run up and coast down. If you have a critical speed, of a machine, which will it will cross. For example, in between from the starting from 0 RPM to say 3000 RPM is the nominal running speed of a motor. So then it will in between there is a background noise. Okay, so there will be in between say 1800 RPM is the critical speed it will cross. So that only at that particular RPM will be there, high vibration. Once it crosses that, then there will be a stationary signal. So that you can capture in the coast up and coast down plot, where you plot the amplitude versus frequency versus time. So at a particular time when the critical speed happens, it will show you in the spectrum. Otherwise, it will not show in the other spectrums. So there is a technique to capture a non-stationary and individual spectrum during the course of the running of the machine. Hope it is answers your question.
Yeah. Thank you.
Okay.
Sure. So thank you all very much. That it was really nice that it became an interactive interaction, and that's how basically we learn about everything. Ladies and gentlemen, before we really close down, I have to say that we have organized this on behalf of Indian Institution of Plant Engineers and CVS, that is Council of Vibration Specialists, together. And we would like to give a small brief. IIPE has been more than 50 years old institution in the country, with chapters at several locations in the country, almost all major centers. And in Maharashtra, our Maharashtra chapter has been very active. And we keep conducting many such programs. Of course, during this COVID period, the frequency has reduced a little bit as far as the personal programs are concerned. We have been all doing webinars and online programs. However, we otherwise would conduct several in-person programs with various types of faculties from different industries. The whole objective is that there should be an interactive interaction between different principles, different disciplines, etc. So IIP has been very pioneering doing this, and Maharashtra chapter has been one of the very active chapters in the country. CVS is been, as quite a few of you know already, and some of you are members here. CVS was formed or officially inaugurated on 15th of August last year. And it was formed with an idea that, this vibration by itself is such a topic. There are so many things which are embedded within this one word called as vibration, which is not only machinery vibration, it also encompasses things like structural vibration, any kind of vibration, so many of them. And it encompasses people from industries, people from research institutes, people from the teaching institutions, etc. So we are very lucky that we have the spectrum of all these members. We have the chairs which are looking at different speciality of vibration, and we have very learned people like Dr. Pine, who is our Director General and Secretary of this institution. Dr. Gambhir is our President, and many others. So we would really request that let us get all together. Let us become members in this if you are not already a member, and then let us share this beautiful science and the ideas. Thank you very much.
Thank you very much, Mukesh, for your enlightening session. Of course, this is not my closing speech, but for all those of you who are here, Indian Institute of Plant Engineers also has its own website. And if you just keep visiting the website, you will be updated about what are the various programs that we are conducting off and on. Of course, this particular program, I'm sorry, Mukesh, my apologies for not updating this on the website. Otherwise, normally we always do, but this COVID has given us a good beating, I think. So most of us have become a little on the back foot. And I look forward. Now, we had a very interesting audience of almost about 27, I think.
Very good.
Yeah.
A good response comparatively. Even Dr. Pine, last week you had almost an equal number, which was also very good. And yes, it only shows that all of us are interested in knowing a little more on the science of condition monitoring. With that, we bring today's session to an end. Thank you so much. And do become members of both the institutes.
Mr. Mobile YO1723, what is the name of the person? Request others also to please give your mobile number or email address in your chat box. People who are present.
There was one form which was shared. If it is possible, you can click
Yes,
that.
yes,
You can,
please,
we
please.
can capture the details in that.
Yes, please fill that form so that we get the details.
Yeah.
I put it again.
I could see the names of
Yeah.
other person, but the one person with the name is not visible.
No.
Is a YO1723 mobile. Can I request him to open the video or yeah, Dr. Paine to everyone, acha.
No, that is
Dr. Paine
different.
ka nahi.
Why? We don't know.
Who is the person YO1723?
Maybe that person has left and I mean
Just now he was there. It is there. He is still there.
It's there, but the mic is mute, camera is off both.
Yes, yes, yes.
Okay.
1723. Please tell your name.
It's Doctor. That is yours, Paine?
Yeah, Ashish Garg.
Okay. It's all right.
Okay.
Yes, thank you, Ashish.
Okay.
Thank you very much.
Okay. Thank you.
Thank you, Mukesh ji. Very nice.
My pleasure, sir.
Thank you, Mukesh.
Thank you very much.
You continued nearly
Very interesting talk, Mr. Mahesh, Mr. Mukesh.
1.5 hours.
Good to know everybody. Good to know new people now, and we will be in touch.
Yeah.
Actually, I got disconnected in between when I was trying to speak with Dr. Lokesh Saab. We'll speak, sir, later on. Somehow my computer got disconnected. Okay.
All right.
Okay. Thank you, sir. Thank you, everybody.
Okay. Thank you.
Mr. Mukesh, are these slides available separately? Can you share it?
Yeah, I can do that.
Mukesh,